the scribe's oath on your screen.
Excellent.
Is that what you see? Oh, everybody's giving me thumbs up. Okay, I got it. Okay, so, this Zoom stuff actually works, sort of. Not bad. And I want you all just to think for a minute. Here we are in the midst of this weird pandemic, and we can all still work. In our industry, we can all still work, and a lot of people can still work. And that is because of tools like Zoom, which we wrote. So in some sense, we, the software programmers, are the ones who have saved the world here from this pandemic. So just keep that in mind. It's our technologies that everybody's using. But here I'm going to go into this talk. So it's a fun talk. This is not deeply technical. I'm not going to put any code on the screen. It's a talk I've given many, many times, and it's mostly for after dinner, after a beer or two, and everybody wants to just kind of settle down and listen to some guy yammer. So I'm going to yammer. Now, oh no, I'm not going to do that slide because I can't get everybody to stand up. And I'm not going to talk about the scribes. I want to talk about this. I'm going to go through a bit of the history of software. And I'm going to start way back in 1936. And there's a little blue arrow there. That's where I come into things in 1952. That's when I was born. And we're going to go all the way to today. And then if we have time, we'll extrapolate out to the future and see what life may hold for we programmers, for us programmers. See if I can get the grammar correct. So we go back to 1936. We could go back further. We could go back all the way to Babbage or something like that. But 1936 is a good place to begin because this is when Alan Turing writes his paper. And oh, by the way, if you have not read his paper, then there is a book you should read, and I'm going to get it out for you here. Where is it? It's on my bookshelf. I pull it out all the time. Oh yeah, there it is. Okay, I'm going to put it in front of the camera. And if you can see me, you can probably see the book. It's called The Annotated Turing. It's written by Charles Petzold. You remember Charles. He's the guy who wrote all those, foundation classes for Microsoft and stuff like that in the 80s and the 90s. He wrote this book. Once he got done writing that kind of software pornography, he started writing this stuff. And this is fascinating. What he did in here is he took all of Alan Turing's paper and he reproduced it word for word, but he surrounds it with history and annotations and discussions. And I've read this book twice. I'll probably read it again. It is a fascinating book to read. So there's a book recommendation for you. The paper that Turing writes is an attempt to solve an obscure mathematical problem that was posed a few years earlier by David Hilbert, and we don't need to go into what that problem was. Suffice it to say, it was a problem of solving formulas based on integers, right? Diophantine equations. And in order to address this mathematical problem, Alan Turing stumbles on the idea of coming up with a machine. And the machine, of course, is the Turing machine. And those of you who have studied software probably studied Turing machines sometime in the deep, dark past. But this was a very simple little machine that was not automatic in any sense. It required a human to operate it and a human to interpret it. But the memory and the operations were extremely specific. And he writes programs for this machine and comes up with pretty much the basics of everything that we do. The man writes code in this paper in 1936. And if you read his paper, you will recognize that what he wrote was code. A little bit different from the kind of code we might write, but still obviously code. He invents macros, he invents subroutines, he invents operation codes, he invents symbols. He goes through the whole thing in order to come up with this proof of this thing that David Hilbert wanted proof. And that was kind of the end of that story. What's fascinating about that, however, is how this kept on being the focus of his work. He eventually went on to, win World War II by getting involved with the Enigma machines, decoding the German codes and so on. And the work he had done in his 1936 paper came back to help him with these machines that were now automatic. The elements in these machines, of course, were relays. And those of you who have never seen a relay, there's a picture of one there. It's a coil. And if you run current through that coil, it becomes a magnet. And the magnet will attract a little piece of metal, which you see there at the right-hand side of the relay. And that little piece of metal will pivot and it'll move the contacts you see. It'll change a normally open contact into a closed contact. It'll change a normally closed contact into an open contact. It's just an electrically controlled switch. And it can operate at maybe 10 cycles per second. But with a switch like that, with a little device like that, you can make a functioning computer. And that's exactly what they did in order to work through the Enigma codes and win World War II. Now you might ask, well, why weren't they using vacuum tubes? I mean, vacuum tubes would have been much faster, and they had vacuum tubes in those days. The problem with vacuum tubes, though, is that they weren't mass produced at that period in time. They were unreliable, they were expensive, they were power hogs. And they had these filaments inside them, which if you ran them for more than a few hours, the filaments would burn out. And if you want to make a computer with 1,000 tubes, their filaments are going to be burning out every 2 minutes. So it was very difficult to get vacuum tubes to work, which was a shame because the vacuum tubes could go 1,000,000 times faster than the relays could. But they couldn't get them to work until later. By about 1942, they had the rudiments to get a vacuum tube computer up and running. And they actually did kind of get this Colossus thing working, but the war had already been won and nobody cared. And that takes us to 1945, where in Manchester, they build what is arguably the very first stored program, real electronic computer made out of vacuum tubes. And the very first programmer of this machine was Alan Turing. He keeps coming back into this story. Now, this was a real computer. Not a big computer, not a powerful computer, but a real electronic computer. The memory that it used was mercury delay lines. This is a picture of a bunch of mercury delay lines. Mercury delay line is a big tube full of mercury with a speaker on one end and a microphone on the other. And you pump bits into the speaker and they travel through the mercury at the speed of sound, and then they hit the microphone on the other end and you electronically wrap those bits back around to the speaker. So essentially this is rotating memory. Think of it kind of like a disk, except that there's no disk. Now, they got these things to work, but they were really unreliable because they're filled with this liquid. And every time a truck went by on the road, it would scramble all the bits. So in the end, they opted for a different memory, which was cathode ray tube memory. Cathode ray tube memory is really interesting. This is, some of you probably don't know what a cathode ray tube is. Others of you probably do. It's a television screen, except not the television screen that we're used to today. It's the old television screen. And some of you will remember, back in the early days of television, the 1970s or 60s, when you turned off the TV and the picture didn't go away right away. It just kind of slowly collapsed into this dot that stared at you for 60 seconds or so. And that's because the image was painted on the screen by an electron beam, and the electron beam was the product of a vacuum tube. The cathode ray tube was a vacuum tube. It had a filament at the end, it had an electron gun, it would spray electrons on the screen and make the screen glow. One of the side effects of scanning an electron beam across the screen is that it would deposit charge on the screen. And the next time the beam swept by, it could detect that charge there, and you'd actually see that in the current of the beam. You could put a little amplifier on the electron gun and see that, oh, there was a drop in the current because there must have been charge deposited there on the screen. And so it was a kind of memory device. A memory device that would allow you to paint bits on the screen visibly. You could see them. Alan Turing's output device was the memory of the computer. He would read his results on a screen by looking at the bits in memory, literally, physically in memory. They got this to work. And this was the time when Alan Turing started really writing some interesting programs. Now, you gotta put yourself in this guy's shoes, right? It's 1945. This is the very first digital electronic computer. There's no language, no assembler, certainly no Fortran, no COBOL, nothing like that, but not even an assembler. He's got to program this thing in binary, right? He chooses a radix that is convenient for him, which was 32. He worked in base 32. Most of us are familiar with hexadecimal or octal. Now he wanted base 32. He wrote his programs in binary. And if you've ever written a program in binary, you know what kind of a challenge that is, because you have to do all the address arithmetic. And then if you ever insert an instruction somewhere, you've got to change all the addresses and redo all the instructions, and you have to do all that binary math correctly. So it's a non-trivial exercise. And in the midst of this, he spends about a year writing code to solve a bunch of interesting mathematical problems that were interesting to him. Nobody else cared, but he cared. And he would read the results off the memory screen in base 32. Now, think of what he had to do here. He wanted to deal with real numbers, not integers. A computer is an integer machine, right? It doesn't know anything about real numbers. So he had to invent a floating point package. Anybody out there ever write a floating point package? That is a non-trivial thing to do. Having written a couple in my life, that is a non-trivial thing to do in a good language. In binary, it's a furiously difficult thing to do. He writes a floating point package. He invents the concept of the subroutine. The machine itself did not have a stack. It did not have a subroutine call instruction. He has to cobble that together out of simple code. He invents the notion of a stack in order to do that. He uses integer add and logical not to do subtractions. The machine could not subtract, it could only add. This is a very, very primitive machine, and he writes a lot of code in binary in this machine. And then he writes a document. Actually, he gives a speech, and the speech got transcribed into a document. But the speech he gave has a number of fascinating quotes in it. Here's one. We shall need a great number of mathematicians of ability. How did he know? Because there will probably be a good deal of work of this kind to be done. How did he know? Now, I don't think he had any idea what was to come. I think if Alan Turing could look at the industry today, he would be as surprised as most of us are. But he could see from that vantage point in 1945 that they'd need a lot more than just one guy writing code. And he called them mathematicians of ability. Is that what a programmer is? Is a programmer a mathematician of ability? I mean, look around. Is that what we are? Mathematicians of ability? Well, that's what Alan Turing thought we were going to be. There's a certain argument to be made in that towards that goal. But he went on in this speech to then say this, and it's remarkably prescient. One of our difficulties will be the maintenance of an appropriate discipline so that we do not lose track of what we are doing. Now, that's a good statement. I imagine there's a few of us out there who have lost track of what we're doing from one point to the next, possibly because we did not maintain an appropriate discipline. But it's fascinating to me that in 1945, Alan Turing, after writing a bit of code, could look into the future and say, yeah, geez, we're going to need a lot of guys who can do this, and they better be good at it, mathematicians of ability. And by God, there better be some disciplines or they'll never get anything done. That seems to me to be a remarkable statement by Alan Turing. Mathematicians of ability, a great number, appropriate discipline. And so now we begin our historical tour. The historical tour begins in 1945. The number of computers in the world is on the order of 1. There were a couple within a few months, there were more than one. The Ace was the first, probably. There's a few other contenders. People like to argue about that. But the number was on the order of 1. The number of programmers in the world was on the order of 1. Let that one sink in. There was a time within one man's lifetime from now, going back that far, where there were no programmers at all. And then there was one. And that was Alan Turing. And there are some people who like to think that maybe it was someone else, but okay, let's say it was Alan Turing. One computer, on the order of one computer in the world, on the order of one programmer in the world, and then what happens? Well, the 1950s come along. And that cathode ray tube memory thing, that's just not going to work, right? Because you can only get 1,000 or 2,000 bits on the screen. And they needed more bits than that. So they come up with this idea for core memory. Now, the picture you're seeing on the screen is a picture that I took. In fact, here, I'll get you the core plane. Great thing about doing these talks from home is that I've got all my props here. This is the core plane. You can see it. I'm looking right through it. I bought this when I was 16 years old. It came from an Army surplus shop. I think it was probably used in a radar installation in the 1950s. There are 16,384 cores on this little grid. Right? That's core memory, 16,384 bits. 2 to the 16th bits. 2 to the, 16. Let's see, I can do that math, right? 2 to the 15th. Oh well, anyway. These little cores, you can see them on the picture there. They are woven into those wires. Now, the cores are made of a substance called ferrite, which is powdered iron mixed with clay and then fired up and melted and then turned into these little rings. The rings can be magnetized. They've got iron in them, so they can be magnetized. And the way you magnetize them is to run current through those wires. You notice the XY grid of wires? So magnetism is one of those cute little things that if you want to magnetize a core, you have to run a certain amount of current through that core. If you run half the amount of current through the core, it won't magnetize it. You have to run the full amount. So what they would do is they'd run half the current horizontally and half the current vertically, and that would select a single core, and that core would be magnetized. Now, of course, you can magnetize something in 2 directions. You can magnetize it north-south, or you can magnetize it south-north. And that just depended on the direction you ran the current through the wires. So you could set the cores into one of 2 states, 0 and 1. And that's how they wrote this memory. Now, the way you read the memory is to force the core to the 0 state. There's a 3rd wire in there that you can barely see, and it actually snakes through every single core on the plane. And if the core flips its state, it will induce a small current into that wire, which you can detect. So if you force the core to 0, if it was already 0, then it won't flip and there'll be no current induced on that wire. If it was a 1, it'll flip to 0. That will induce a current on the wire, and you will have detected that you had a 1 there, and then you had to write the 1 back in. So it was a 2-step process. Fascinating. This technology persisted in computers well into the 80s. Even into the early 90s. I was working on machines that had close to 1 megabyte of core memory in the early 90s time frame. Although by that time, we were starting to see different kinds of memory. The vacuum tube also came into its own in the 50s. They were getting mass produced. They became reliable. They became relatively low power. And the idea that you could build a significant machine out of these things tickled a few companies, and some companies, one of them called IBM, started to make machines out of these horrible devices. And I'll tell you why they're horrible in a little while. This was the era of Fortran. Fortran was invented in 1953. I am 1 year older than Fortran. I claim that as my birthright. We would write code in this language, and I did write Fortran. Oh, yes, I did, Fortran 4. Maybe some of you out there did too. There's a little bit of Fortran code on the screen. Take a look at line 703. That's an if statement. If IA plus IB minus IC. You see that I there? That meant that that was an integer. Any variable that began with the letters I through N was an integer. Anything else was a floating point number. I think we called them reals in those days. The quantity inside parentheses would be evaluated. And then if that number was negative, it would jump to line 777. If it was 0, it would jump to line 777 as well. And if it was positive, it would jump to line 704. That was the if statement. That was the only if statement. That was how you made decisions in Fortran. I won't belabor you with the rest of the language. It was a very, very primitive language. But boy, it was something to, in those days, to program in. And what did we program in? We wrote our code on that green stuff down there. See that green thing? That's a coding form. We would write our code in pencils. Of course, we had no screens. In those days, programmers could not type. Programmers did not know how to use a keyboard in those days, right? You wrote it in pencil and paper, and then you handed it to people who would punch it on these cards here. Yeah, see, look at me, I got a deck of cards. That's an actual program that one of my friends wrote a long, long time ago. Actually, it's a chunk of a program. And I've kept it around for, well, I don't know why I kept it around, probably just to wave it at you. But that's where we wrote our code. And then we would take that code down the hall and hand it to the operators, and they would compile it, usually at 3 in the morning. You know, the programmers were not allowed to touch the computer. You were not allowed into the computer room. Only the operators could go into the computer room. And the operators were a different species of human. They kept guard over that room and would not let you in. There's a lock on the door. Only they had the combination. If you wanted to have a compile run, you would approach the door and make the necessary gestures of obeisance. And then you would put your deck in a little basket and back away. And then this arm would come out of the computer room and take your deck into the bowels of that hallowed sanctuary, where it would sit until 3 in the morning. That's when they would run the compile. Now, why didn't they run the compile right away? Well, there was only one computer, and it was busy, and it had to be kept busy 24/7. That thing had to be running all the time. They couldn't not run something because the machine itself cost several $1 million in 1950 some dollars. So that was real money back then. And you just kept that thing busy all the time. So it was doing bill of materials, and it was doing payroll, and it was doing general ledger, and it was doing all this stuff. At 3 in the morning, the operators would finish all the batch jobs. They had nothing left to do, and they'd get all the programmers' decks, and they'd stick them in the card reader, push a button, and then they'd go get coffee. And the compiles would run, and they'd print out. The compiles would run, and they'd print out, and the operators would tear off the listings and stick them out on a desk, on a table outside the computer room. You'd come back in the next day, and you'd take your listing to your desk, and you'd open it up and realize you'd forgotten a comma. This was the life of a programmer in the 1950s, the 1960s, even into the early 70s. You did not type your code. You wrote it in pencil. Other people punched it. You might get a little bit of time on the computer once a day. But that was the way we worked. And the only way to be efficient in that environment is to work on 10 programs simultaneously, so that you had this long kind of conveyor belt of programs going into this horrible process whereby you'd get a compile once a day. You desk checked your code really well. Because if you forgot a comma, it was a 24-hour turnaround. That was going to cost you a day. So,
Bob, I don't know if you're watching the chat, but you've inspired a great conversation about Fortran 77 and such.
oh yes, F77. Well, that came along later. Let's see how astute our viewers are. Anybody know who wrote the Fortran 4 manual? You could put the name on there. If you get it right, I'll give you a little ding.
Come on, somebody needs to be.
This was the years of Lisp. Lisp was invented in 1958, right? By the way, I mean, Lisp is still an active language. People are actually doing Lisp. No, it was not Grace Hopper. It was Daniel D. McCracken.
Release McCracken?
Daniel D. McCracken was the author of the Fortran 4 manual. So Lisp was one of those languages that was conceived and run early on. This was a fascinating time. The machines looked like this. This is an IBM 709. It was part of the 700 series. They made as many as 140 of these machines. They sold for millions of dollars. In fact, IBM didn't sell them at all. IBM would only rent them to you for thousands of dollars a month, tens of thousands of dollars a month. And companies who could afford it were only too eager to get them, right? Notice who's programming this. This is during the era when women were programmers. During the 50s and into the 60s and even into the early 70s, the number of women in our industry was fairly large. When I started programming in the very early 70s, the first job I got was at a programming shop where about 1/3 of the programmers were women. 10 years later, I was working somewhere else and there were almost no women at all. Something weird happened in the 70s, but we'll get to that a little later. In the meantime, take a look at this machine. These machines were horrifically expensive. You could run Fortran on them. You could run Lisp on them, although most people programmed them in assembly language because that was the most efficient language to work in. Somebody had mentioned Grace Hopper in the chat. Here she is. Grace Hopper was a woman who got involved in the Navy with radar installations and the data processing that was necessary for radar. And that led her into the whole computer world as that kind of grew. And she became what we would now call the CTO of Sperry Rand and UNIVAC during making the UNIVAC machines. She became deeply concerned that programs were hard to read. Imagine that. And she came up with an idea. And the idea was to program in a very disciplined, formal form of English. And she came up with the common business-oriented language, COBOL. The idea behind COBOL was that you would write your programs in English. Anyone who could read English could read these programs. It was terrible. I mean, the idea was a beautiful idea. The implementation was awful. As an old COBOL programmer, I can attest that it nearly destroyed my brain, and I never want to go back there again. Grand idea, terrible implementation. We learned the hard way that programming is not English. Programming is not natural language. Here's a little picture of all the programmers of the ENIAC at Princeton. This was the American computer. This was not a stored program machine. This was a machine, yes, Siri, thank you, Siri. This was a machine that you programmed by wiring things up. And you can see that's what they're doing there. This was not a machine to be trifled with. These women knew what they were doing. This was a funny time, right? Men built hardware. Women were the clerks. They could write, they could do the programming. That was the mindset. That's why women became programmers early on, right? It was considered a kind of secretarial function. Little did they know. By now, it's 1960. The number of computers in the world is on the order of 100. It's probably more like 500 or 700 or something like that. But I'm using big O notation, which means you can just kind of fudge it and doesn't care at all. So something on the order of 100. And the number of programmers in the world is on the order of 1,000, probably more like, 9,000. A lot of programmers in the world by 1960. Although still this funny low number compared to today. Now, notice that there's an order of magnitude more programmers than there are computers, and there's a reason for that. In these days, there was no operating system. There were no libraries you could download. There were no frameworks. If the code was in the computer, it was because you wrote it. Anything in that computer, you wrote. Every bit you wrote. And it takes a lot of programmers to write the bits that go into a computer to keep it running all the time. So we needed about 10 times as many programmers as there were computers. Who were these programmers? Well, they didn't go to school. There weren't any degree programs to learn computer science. Computer science wasn't even a science in those days. So these programmers were actually taken from industry. They were engineers and scientists and mathematicians who already had jobs. And their employers would come to them and say, hey, you want to try this new thing? We need people to program these computers. And a few of them would move in that direction. They would say, oh yeah, that looks like the future. Now, these were not young people. These were not people in their 20s. These were people in their 30s or 40s or 50s. These were old people, people who understood the business, understood the discipline of being in a business. They understood projects. They understood deadlines. They were professionals who were changing profession. And then came the transistor. And the world changed overnight. That vacuum tube got replaced with something that was the size of your little fingernail. And it drew no power, almost no power. I mean, compared to a vacuum tube, just to keep the filament going would take 1 watt. These things would take milliwatts of power. They were very fast, very reliable. The filaments didn't burn out because they didn't have filaments. And almost overnight, the industry changed. By 1965, IBM was building 1401 computers. That was the model number, 1401. They built 10,000 of the doggone things, and they were so cheap that you could rent one for $2,500 a month. That put it in the range of most mid-sized companies. Most mid-sized companies could now get a 1401 computer, rent it, and then get some programmers to program their payroll and their inventory and their general ledger and automate their processes, which is what everybody was doing in the mid-60s. This was a fascinating machine. IBM made the decision that their target customers were businesses, and businesses worked in decimal, not binary. So this was a decimal machine. Oh, it still used bits, but it used them in binary coded decimal. Every digit was 4 bits. And they would only take them up to 9, 0 to 9. Didn't go up to the other digits that you could put in 4 bits. It was so decimal, in fact, that this machine shipped with 4,000 bytes of memory. Not 4096, 4,000 bytes of memory. Fascinating machine. You could run Fortran on it. You could run COBOL on it. Most people programmed it in assembly language because high-level languages in those days were like a luxury that hardly anybody could afford. So now, by 1965, the number of computers in the world has increased by 2 orders of magnitude. Now it's on the order of tens of thousands. The number of programmers in the world, it still need 10 times as many. Now there's hundreds of thousands of programmers. In the span of maybe 5 years, the number of programmers in the world increased by 2 orders of magnitude. Fascinating, right? Massive amounts of programmers needed to run these machines.
And that's when I was born, so.
Well, I'm 13. Yeah, I come into the picture at this point. I'm 13. I've already chosen my career. At 13 years of age, I knew exactly what I wanted to do. And I learned that because of this little machine here. My mother got me this machine on my 12th birthday. This is a little digital computer. It has 3 flip-flops. You can see the ones and zeros in the little display over there. I hope you can see them anyway. It's got 3 little flip-flops. Over the top, it's got 6 AND gates. They're entirely mechanical. There's a nice little mechanism here that will cycle the machine, and you program it by putting little tubes on these pegs here that will block these AND gates from going in. And it's a 3-bit finite state machine. A 3-bit finite state machine with 6 AND gates. You could program it to count up, count down, add a couple of bits, subtract a couple of bits, and the machine absolutely fascinated me. I got this machine on my 12th birthday, and within a matter of weeks, I knew what I wanted my career to be. I was going to be a programmer. Now, where the heck were they getting all these programmers from? There weren't enough engineers and scientists and mathematicians. They'd already exhausted all those. So, and there weren't any computer science grads in 1965. They weren't coming out of university. So they were actually drawing the computers from their existing staff. They would use the best and brightest accountants and planners and marketing people and stuff like that. They would try and find people with an aptitude. And thus was born the infamous aptitude tests that would be passed around inside a company. And people would take these aptitude tests to see if they had the aptitude to be a programmer. These tests were actually terrible. They didn't identify programmers, but they did use them to recruit lots and lots of people to be programmers. And once again, these were not young people. These were people in their 30s and 40s and 50s. They didn't want to take kids and have the kids use these $1 million machines. They were going to take mature people and to run the processes of their companies. They weren't idiots back then. They got the old people to do it. Though they may not have been mathematicians, they were experienced, disciplined professionals. And I like to think that Turing would have approved of the choices. This, again, is an amazing time. IBM, by this time, is now producing 1,000 IBM 360s every month. This is an IBM 360 on the screen. I used to work on these machines. Beautiful machines. Every science fiction movie with a computer in it was modeled after these machines, because the lights would blink on that thing. Lights everywhere. And if you were a good programmer, and you knew your code, you could study the way the lights blink and debug your code. And right as it was running, you could see what process was running and how well it was running. There was a lot of information on those lights. This is also the time when OO was born. Ole Johan Dahl, Christian Nygaard, working in Oslo on an old, horrible machine in Algol, stumbled across object orientation almost by accident. And the story is well documented in this lovely book here. Let me get it out. Where is it? Ah, yeah, here it is. Structured Programming, Academic Press, 1972. This is the book where Dijkstra says go-to might not be such a good idea. This is also the book where Ole Johan Dahl describes how they invented object-oriented programming, although they didn't call it object-oriented programming. The language they invented was Simula 67, and objects were born. Dijkstra invents structured programming in 1968. He writes a paper, go-to statement considered harmful. He didn't put that title on it. The editor of the magazine did. It was actually a letter to the editor. But he outlines why go-to is harmful. I'm not going to tell you that story here, just to give you the idea that critical things were invented in this decade. What else was invented? Oh, little things like C and Unix. This is when Ken Thompson and Dennis Ritchie stole time on a machine, a PDP-7, up on the PDP-7 or a PDP-3 or something like that, up on the 7th floor of AT&T, Bell Labs. Wasn't AT&T then, it was Bell Labs then. And they invented a couple of little things, the C language and the Unix operating system. Nobody told them to do that, by the way. They just kind of hacked it away. Digital Equipment Corporation had been founded and was starting to produce these ridiculous machines, these mini computers, and they were cheap. You could buy a PDP-8 for the equivalent of $20,000, right? And that was nothing. That was nothing. A company could buy one of those, 4K of core, 12-bit words, 1 microsecond cycle time, roughly. You could get a lot of work done on a PDP-8. I spent a lot of time on PDP-8s. Beautiful machine to program. You can see one over here. Little thing blinking over here. That's actually not a PDP-8. That's a PDP-8 simulator. It's got a Raspberry Pi running in there, simulating a PDP-8, which of course simulates it faster than any PDP-8 ever ran.
I was going to say that seems like a little overpowered for that kind of computer.
Yeah, it definitely is now. And then what have I got to do? And I've just got to sit in there blinking to keep me happy and smiling. So by now we're into the 70s. The number of computers in the world is on the order of 100,000, probably close to 1 million by this time. The number of programmers in the world is still 10 times too large. Still 10 times. It hasn't caught up yet because, once again, there's hardly any frameworks. There's hardly any subroutine libraries. There's hardly anything to download. There are operating systems by this time. But we still needed more programmers than computers. Who were these programmers? Wait, now, look at the time frame here. This is 25 years. And in 25 years, we have gone from one programmer to millions, hundreds of thousands, maybe 1 million, maybe a little more than 1 million. That's a hell of a growth rate. That's an enormous growth rate. Who were these programmers? Hundreds of thousands of computers, millions of programmers. Who were they? Well, one of them was me. This is me at 18. I already had a job as a programmer. I got hired early on. I'd already taught myself Fortran and COBOL and PL1 and a number of assembly languages. And I managed to steal time on computers wherever I could get to them. I'd go to the sales office of Digital Equipment and sneak in there and play with their PDP-8s. There was a client service bureau near my home. They had IBM 360s. I'd steal in there. I got a job as an offline printer operator printing junk mail. And there's an IBM 360 in that area. And I used to bug the programmers and learn a lot about it. Eventually got a job as a programmer at 18. Didn't go to college, didn't get a degree. This is my route that I went. And I wasn't alone. However, tens of thousands of CS and EE grads started pouring out of the universities. This is when the CS degrees were available. The computer science degrees finally became available in the 70s. And they're just an enormous number of young people pouring out of the universities. And they all had something in common. They were all ridiculously young. And they were almost all male. For some reason, the graduating classes were graduating young men. Young women were not graduating. The reason behind that remains a mystery to me to this day. At my first job, there were about 24 programmers. Most of them were in their 30s or 40s. Wasn't a young person's game back then. Half them were women. A third to a half of them were women. But just a few years later, in 1980, I worked at a place that had 50 programmers, all of us in our 20s and early 30s. 3 of them were women. Something happened in the decade of the 70s, something weird. And what it was, I don't know, but here's a picture of it. That red line you see is the women in computer science. The 3 green lines are the women in other STEM fields. Something happened in our industry. Something happened to chase the women away or something. It's not clear to me what it was. And maybe there's a couple of women out there that could chime in and tell us what it was. Although I've asked a lot and they all kind of shrugged their shoulders. I don't know either. Something happened. But today in the Western world, the number of women in computer science is well under 10%, and it's probably closer to 3%. Something's wrong. Don't know exactly what it is. Something's wrong. But businesses had to have programmers, and the only programmers they were going to get now were a whole bunch of young, impossibly stupid, testosterone-driven young males. And although they may not have been very disciplined, they made up for that with an awful lot of energy. These are the idiots that would work 80-hour weeks. And they were cheap. My first job as a programmer earned me $6,800 a year. That was an enormous amount of money for me back then. Nowadays, of course, it wouldn't be worth very much. But, I was a young kid. I barely had a car payment. Still living at home. $6,800 a year. That was just a tremendous amount of money. Now, remember, up to this point, the programmers in the world had been disciplined professionals. They didn't need a lot of management. They didn't need a lot of process. They knew how to manage their time and communicate and work together. They understood deadlines and commitments and what to leave in and who to leave out and the whole Bob Seger song. They knew all that stuff. But now, and they had worked miracles. These older people had worked miracles. It was while they were programming that the virtual memory operating system was invented. It was those people that put us on the moon and did the Mercury and Gemini and Apollo projects. It was those people who invented structured programming and functional programming and object-oriented programming. It was those people who wrote Fortran compilers and COBOL compilers and Algo compilers, Lisp and C and Unix. The major lifting had already been done, because original programmers could do big things. What process did those original programmers use? Well, we can't really call it agile because it wasn't called agile then, but it was something very similar. And in fact, nowadays, people say that agile is the process used by disciplined professionals observed in the wild. If you go back in time and look at what those guys were doing, they were working in iterations. They were working in short iterations, right? The Mercury space capsule programmers wrote their unit tests in the morning and made them pass in the afternoon. They were doing a kind of test-driven development, and they had one-day-long iterations. Other projects back in those days used longer iterations, maybe 1 week, maybe 2 weeks, but the idea was there. This thing that we call agile, that we think was invented in 1999, right, was actually in use in the 50s and the 60s. It didn't have a name and it didn't have the formalism to it, but it was there. But now, hordes of young testosterone-driven boys flood into the field, and they need some kind of discipline imposed upon them from above. They need a process. And management, getting some kind of control over those boys, decides that this picture would be a good picture to place upon them, this waterfall idea. And the waterfall era came into being in the 1970s. It lasted for 30 years. For 30 years, we lived under this shadow of waterfall. Now, I remember the first time I read a paper on this, and it was in the early 1970s. And here's this paper that's saying, you could do the analysis first, and then you could do the design, and then you could do the implementation, and you could put dates on those. And then you would know when the analysis was done, you would know that you were a third done. And when the design was done, you would know that you were 2/3 done. What a wonderful thing. You could schedule your software that way. And I read that as a young man, and I thought, yeah, that's great. We have to do that. Of course, it didn't work out all that well. And eventually, in the end, we changed our idea. But something else was going on. How many programmers do you think are in the world today? And the number is huge, right? I mean, every city has tens of thousands of programmers. If I go to a user group to do a talk, I'll get, 200, 300, 400 people show up at just anywhere, in any city, sometimes more. There are a lot of programmers in the world. I think maybe it's on the order of 100 million. You might disagree. Maybe you think it's 50 million or 20 million. Maybe you think it's 200 million. I'm not sure how we'd count them, but I'm going to use the number 100 million to do a simple little mathematical experiment with you. In 1946, there was one. In 2020, 74 years later, there's 100 million. How do you get there? What kind of growth curve is that? Is it linear? No, it's not linear. It can't be linear, right? It's got to be exponential. Everybody knows it's exponential. Okay, well, if it's exponential, we're programmers. We happen to like the base of 2. So let's just find out what exponent of 2 is 100 million. 2 to the 10th is 1,000, 1024, but close to 1,000. 2 to the 20th is 1,000,000, close to 1,000,000 anyway. 2 to the 7th is 128, okay. No, 27. 27 is the exponent of 2 that will make it 100 million. So there have been 27 doublings of programmers since 1946 up to now. Now that's 74 years. How many doublings, how many years per doubling? Well, 27, 74, 3 divide, it's about 2.5, isn't it? Does the number of programmers in the world double every 2.5 years? Is that really what's going on? The answer to that is no, because in the early days, that first decade, it doubled a hell of a lot faster than that. Because the first day there was Alan Turing, but a day later there were 5 guys, and a week later there were 20 guys. And a month later there were 100 guys. The doubling rate was enormous in those first decades. And then it slowed down. There is a fair bit of evidence now to suggest that the doubling rate is about 5 years. The number of programmers in the world doubles every 5 years. Now, that has a number of interesting implications. One of those implications is that half the programmers in the world have less than 5 years experience. And this will always be true as long as we're doubling at a rate once every 5 years, which leaves our industry in a state of perpetual inexperience. Remember how Alan Turing said we needed mathematicians of ability? You don't get that ability in the first 5 years. Half the programmers in the world do not qualify. Probably you get that ability maybe after 10 years, maybe. Now, a lot of programmers don't even make it to 10 years because a lot of programmers get into programming so that they can go into management later. They think that's the career path, which is fine if they want to do that. There are a few of us, however, that remain coders for a very, very long time. Unfortunately, there aren't enough of us. The hordes of young people pouring into the industry overwhelm the people with any kind of experience at all, which means that most of the code in the world is written by people who don't know what they're doing. And this will remain true as long as we keep doubling at this goofball rate. Now, there's only 8 billion people on the planet. There aren't that many doublings left. You can do the math on this. It's, something that you could hold close to being on your hands. One of those doublings is going to have to all be women because right now we're ignoring half the planet. Right? So somewhere in there, the women are going to have to join in. Is it possible that 10% of the world could be working in programming? Is that possible?
Yes.
Is it going to require that significant fraction of the human population to keep things running? I want you to look around right now. Just look around and start with your own body. How many processors are on your body at the moment? Now, I'll do this with you, with me. And the first thing, obviously, to take out is your phone, which I don't know why we call it a phone, because this is not a phone. Anyway, how many processors are in this? Well, I mean, the machine itself has probably got one for the screen and one for the cellular radio, one for the Bluetooth, one for the GPS. There's probably a few others in there. I don't know, a bunch of computers. But the one that really gets me is the one in the case. There is a processor in the case. There's code running in the case because the case has a battery and the battery has to be charged. And the computer controls how to charge that battery and it communicates with the phone about the charge of the battery. There is a program running in the case. But that's not the only computer on my body. Oh no, because I have AirPods. I've got AirPods. Oh heavens, and they're not the pros. Sorry, these are just regular AirPods. But oh look, there's two little things. They both have program processors in them. There's code running in both of them, probably multiple processors in both of them. And of course, there's a processor in the case. Okay, and I've got, oh heavens, I've got my Apple Watch. How could I forget my Apple Watch? How many processors are running in that? I don't know. And I've got my car key. There's my car key. There's a processor running in that. Any other processors on my body? I don't know, but look around me. How many processors are running in this room? How many processors are running in your room?
Several hundred, I'm sure.
The thermostat?
A lot of them just in the your little back behind you over your shoulder there. You got a little.
Oh yeah, I got a flight simulator.
No,
back
you got some little device. I think it's bigger on the inside though. What would that be? Fully behind you, the other side.
Oh,
the other side.
Oh yeah, the TARDIS.
Oh yeah. Oh, is that what that is?
Bigger on the inside than the outside.
Yeah, it probably has a lot of processors.
Dimensionally transcendental. Yes. Okay. The number of processors running around you right now is huge. A person in the Western world cannot do anything without software being in the middle of it. You can't microwave a hot dog. You can't wash your dishes. You can't wash your clothes or dry your clothes. You can't make a phone call. Can't watch TV. Can't drive your car. Can't buy anything. Can't sell anything. There's no law that can be passed or enforced. No insurance policy can be claimed or underwritten. Nothing happens in our society without computers today. This was not true 30 years ago. 30 years ago, lots of things happened without computers. Today, nothing happens without computers. Your grandmother, if you still have a grandmother, uses a computer every minute of every day because there's nothing you can do in our society without using a computer. You and I write the code for all of those computers, and our society depends on them for its existence. Civilization is now in a place where it cannot function without us. And that's growing at a crazy rate.
Oh yeah, Jack points out even your credit or debit card probably has some processor capability too.
There's probably a processor in there.
Yeah.
That's a frightening thought. This leads us to the disaster that must come. And we've had some hints of that disaster. It hasn't happened yet, but we've had hints. The 737 MAX is a good hint. You know, several hundred people were killed by what amounts to a software failure. There was some hardware involved too, but there was a fair bit of software in the mix as well. And you may remember things like Night Capital, you know, where they lost a $500 million in 45 minutes because some software guy did something stupid. Or how about the Toyota cars, right? That had a little stack problem in their processors, and the accelerator would go full on and the brake wouldn't work. Killed about a dozen people. You and I are killing people. Programmers are killing people. The little bugs that we make, right? Because we didn't calculate the stack size properly, you know, kills people, loses fortunes. We didn't get into this business because we wanted to kill people. You know, you and I got into this business because we wrote an infinite loop that printed our name once, and we thought, oh my God, that's just so cool.
The power.
Now we're killing people. And you know what's going to happen. Sometime soon, probably, some programmer is going to do something stupid and kill 10,000 people at a shot. And it doesn't take a lot of imagination to think what that might be now. How could you kill 10,000 people in a shot with a missing comma? Well, we're probably going to find that out pretty soon. And when that occurs, the politicians of the world will rise up in righteous indignation, and they will point their fingers right at us, and they will ask us the question, how could you have let this happen? And you might think that they're not going to point their finger at you. You might think that they're going to point their finger at your boss or your company. But we saw what happened. Remember when the CEO of Volkswagen North America was testifying before Congress? Congress asked them this question, sir, how could you have let this happen? Remember, the issue was that there was code running in the Volkswagen that detected that it was on an environmental test stand, and then it would adjust the engine parameters to not emit lots of nitrous oxides. And then as soon as it left the environmental test stand, it changed the engineering parameters so that it would spew tons of nitrous oxides into the atmosphere. How could you have let this happen, sir? And I quote his answer to you. It was just a couple of software developers who did it for whatever reason.
Under the bus.
Under the bus is right. Those software developers are in jail now, by the way. But he took the finger and he pointed it right where it belonged, right at the programmers, because in the end, it was the programmers who wrote that code, who wrote the lying, cheating code. So when the question gets asked, it will be asked of us, and we'd better have an answer for them. Because if our answer is, my boss told me it had to be done on Tuesday. If that's the answer we give them, they will hang their heads in disgust and walk away. And then they will begin to write laws. Laws about what languages we can use and what platforms we have to use, frameworks we have to use, what processes we have to follow, what books we have to read, what signatures we have to get. And we'll all end up working for the post office. I'd like to avoid that outcome. I don't think it would be wise for us to let the government tell us how to do our jobs. So I think we have to get there before they get there. And how do we do that? Well, we need to come up with a set of disciplines and a set of standards and a set of ethics. This is what the doctors did. The doctors did this long before the government got involved, right? They had a real problem with anybody could be a doctor. You could go and operate on someone without any kind of license, and there wasn't any legal consequence, and claim that you were a doctor and kill a bunch of people. So the real doctors came up with a way to organize and a way to license people, and they came up with an ethics and an oath, and they came up with disciplines and so forth. And eventually government came to them and said, hey guys, we need to regulate you. And the doctors handed them all these rules, and government's lazy. So they said, yeah, great, we'll take those, we'll make them laws. And that was how we got our legal medical system. And the lawyers did the same thing, and the architects did the same thing, and even the plumbers did the same thing. You and I are going to have to do this as well. We're going to have to decide what our ethics are, what our standards are, what our disciplines are. We are going to have to decide what we profess. We like to think of ourselves as professionals, but right now we profess nothing. We have no standards. We have no ethics. We have no common set of disciplines. We're pretty much Wild West. And the civilization of the world is riding on us. So I think we're going to have to get ourselves a little organized and figure out just who we are. And with that, I think I will close this session. Thank you all for your attention. I hope you enjoyed it. That's a fun little talk I like to give from time to time.
Yeah, it's definitely fun. It wasn't my fault though.
What did I miss?
Bob, I've had a chance to work on medical software, and it was interesting in part because when I started working on that job, I'm like, wait a minute, I could be affected by this very software I'm writing now.
Yeah, okay. Yeah, the old story of the Therac machine that killed a bunch of patients because of a user input glitch that turned the X-ray machine on. Right?
Yeah.
But there are regulated software industries at this point. There's medical software industries that have a certain amount of regulation. I'm not sure they're wise regulations, but there are. Aeronautical also has certain regulations.
Yep.
But the real regulation is going to have to come from us. We're going to have to figure out what these rules are, what the disciplines are, what the ethics are.
The best regulation of all is what the ancient Babylonians practiced. If you were a bridge builder, your family had to live under the bridge for a year. It's called skin in the game.
Not a bad idea.
Yeah, the best form of regulation is called skin in the game. And the reason the big banks keep getting bailed out and the big corporations keep getting bailed out is because no skin in the game.
Well, maybe I might take that a step back. The reason they need to be bailed out, maybe, might be a variation on that theme.
Need, yeah. But anyway,
no, I hear you where you're at there. Yes.
Your code of ethics is never going to work if it doesn't affect you personally, I guess is what I'm saying. You know.
Yeah, and the way the doctors did that is that if you violated the code of ethics, you weren't a doctor anymore.
Except that they ran Semmelweis out on a rail and he committed suicide. You know, the guy that said that there was these tiny things that made people sick and that it was because of the doctors working in the morgues and then working in the maternity ward that women were dying. And they said, what? No scientist believes in small little things called germs that you can't see and make you need to wash your hands. So unfortunately, you know, I hope you're not Dr. Semmelweis is what I'm saying, Uncle Bob.
Yeah, the story of Semmelweis is definitely a cautionary tale. And you're right. He died penniless. He died demoralized, virtually insane. His ideas were completely poo-pooed by the establishment at the time.
Yeah.
It was 70 years before Pasteur came along and showed the world that, oh yeah, there were these little germs.
Well, and Semmelweis was a jerk about it too, which didn't help his cause because no doctor wanted to hear that they were a murderer.
Yes, well, there you go.
The same thing could happen with software if we're not careful with the messaging, where suddenly the programmers turn and say, hey, you're calling me a murderer. So
Galileo had a similar problem. He was a jerk about his whole thing.
Yeah.
Yep. It's not real surprising that the Pope decided that we got to shut this guy up.
Yep.
Bob, there's been talk through the years of certifications and tests and all those kinds of things. What are your thoughts on that to solve some of these problems?
Well, none of the certifications that I'm aware of right now are worth a snot. It seems to me that if you were going to get a real certification in software, it would be something that would be worth a semester course or two at least. And you know, at the graduate level, long after you had gone through all the basics. I don't know if university is the right place to do that. Maybe a better place to do that is in some kind of apprenticeship context, where you go to a company and you're not allowed to touch business or client code for the first 6 months while you work with a mentor. But you know, something like that, some kind of mentorship or education like that. If anybody out there a pilot, you know what it takes to become a pilot of an airplane? I mean, you have to sit next to a guy who knows how to fly for a long time. And he shows you how to do it. And then after a while, they'll let you fly the plane on your own, but not with anybody in it, just you. Skin in the game, yeah, that's skin in the game. And then once you pass your pilot license, once you get your pilot license, then you can actually fly people around. Can't charge them any money, but you can fly them around.
Well, Bob, I'm assuming you all have similar. We've got some coding schools around here that are very, at least one or two are very cognizant of apprenticeship and programs and stuff, and getting people out into the industry and let them learn on a job with help. And I've seen some excellent results based on that too. People
I'm glad you have. I've seen
who seem to know what they're doing.
Apprenticeship programs as well.
Yeah, I love that, and that should just be the way.
Well, it's expensive. Companies don't want to do it. I mean, you're going to hire these people, and then they're not going to be productive for the first 6 months.
Well,
now, the little secret is they're not going to be productive for the first 6 months anyway.
Exactly.
But
Well,
now
and
they're
it's tough
taking
too
away time
because,
from someone
oh,
else.
sorry.
No,
Go ahead,
I
Rich.
was saying they might take away time from someone else. Oh no, what will we do?
Oh, I was just going to say it's tough too because usually the people who can afford to do internships and apprenticeships are the people who already have a lot of access to resources anyway. So that kind of perpetuates the problem of getting people into software that are struggling to get in, because if they can't afford an unpaid or a low paid internship or apprenticeship, then you just perpetuate the cycle that the well-connected and the well-resourced are going to be the ones that continue to get in the industry. So I'm not disagreeing with you, Rich. I think apprenticeships are great, but making an opportunity to also provide an open door for people who maybe don't have that access through their,
No,
the
no.
resources they just have naturally is super
Well,
important too. And I know places around here do that as well, which is really cool.
I think, Jeff, I think the point, in fact, I'll refer to Roland's comment on here about the building industries and stuff. There's a lot of precedent for having paid internships that make it possible to participate without, you're not going to make the big money yet, but you're going to learn and you're going to be able to live while you're learning. This is a classic. In fact, there's a home improvement show I occasionally listen to on the weekends, and they're constantly pointing out, why are you going off to four-year college and for a degree in literary arts when you can go become an electrician or plumber and get paid to learn how to do it
And earn good money.
and earn good money at it too? Maybe not quite as good as us, but they're not that they're pretty close considering.
This has been Mike Rowe's point for the last, 6-7 years or more, right? We need people in the trades. We need people to, and I think software is more a trade than a profession. I think it's something you can learn without a university degree. I certainly did. And I know a lot of other people who did as well. So.
Yeah. There's some guy that started a company up in Seattle area. They made operating systems or something. I don't think he ever finished college. Maybe.
Now he left a little early to sell his BASIC compiler. That didn't go so well.
Yeah.
Of course, he bought the operating system.
Yeah.
Yeah, for 60 grand. Yeah, the guy who sold it to him, he's probably a little bit upset about that.
Well, maybe he was an investor too.
Well, maybe.
Now, is it true though? Is it true though that he tried to sell it to IBM and they actually said they'd prefer to license it?
I don't know if that's true.
Okay, I didn't. That's why I, prefaced that. But I've heard that it would be very interesting if it was true. Sometimes you just have to be lucky, not smart. You just have to be smart enough to capitalize on the luck when the time comes, right?
Yeah.
Smart and luck together. It's a good formula.
Indeed. Lucky I wasn't smart enough to, oh wait, no, I don't know what it was. I had a point there. I don't know what it was going to be. Anyway, do people continue does anyone still have questions? Because, this is not far off from where we'd wrap up normally if we were an hour later, except we're an hour earlier now. And that's a good point. Trevor, Trevor points out Pluralsights can be better than classes. And yeah.
They can.
I use Pluralsight a lot, but I had a question for Bob. What are your thoughts on low-code solutions and the citizen programmer?
My thoughts on low-code solutions and the citizen programmer. I'm not sure I understand that at all.
Trevor, is that kind of like where what we've done before is the drag and drop interface where you can take modules that accomplish something and drop them on?
Yeah, that's what the whole movement is. Low code, everything's drag and drop, and you configure a few things, and you have a working program.
Every time I've heard it, it sounded good, and it's never worked.
Yeah, I've never seen it work as well as it's been sold.
95%.
It sounds like the ideas that have cycled around the industry for decades, where the great goal is to get rid of programmers. If we could get rid of programmers, life would be good. So let's come up with a way that analysts can draw diagrams, model-driven architecture, this was called back in the 90s, right? Let's come up with a way that architects can draw diagrams, and then we don't need the programmers. We'll just have some engine that interprets them. And the problem with that is that programmers are detail managers. And somebody's got to manage the details. And no drag and drop interface can. Because at some point, you've got to write that damned if statement that has to figure out whether the text file ends in a \n or a \n\r. And there's no way around that. Somebody's got to fiddle with all the horrible little details, and those people are called programmers.
How about pairing programmers with artificial intelligence?
Yeah, I'm not really thinking that's a thing. like I have a prediction on self-driving cars. I don't think we'll ever have them, or at least not in the next 20, 30 years. There can be little cars driving in very constrained environments, but I don't think we'll have the Uber that you call and it comes up to your house with nobody in it and it takes you to the mall and then drives away. I don't think that's going to happen for a very, very long time.
Chris, good comment, but that might apply to us too, just so you know. Chris says AI, true AI, is a myth. I'm proposing that natural intelligence may also be a myth in that regard, in the same way.
Well,
we're just the product of our experiences.
Somebody's going to leave out the semicolon. They have to.
Pretty sure I left one out today myself, to be honest.
It's not a syntax error.
It's interesting you brought up the 737 MAX too, because to me it's a reminder that these are human problems and not technology problems. And I think that's one of the fundamental issues we have in our industry is so many people think technology is the solution, but usually it's a solution masquerading as a requirement. When I hear product people saying Kafka and Kubernetes, I just want to quit and go like fishing, sort of, Office Space style. But the 730 MAX was a conglomeration of social issues where the 737, do you remember when it was built, Uncle Bob? First design?
Oh, heavens, my goodness. Sometime in the 60s.
Right. And so they wanted to keep getting, better fuel economy and better, all these different things. So anyway, they ended up with these engines that were really, really wide and really close to the ground. And they were so wide that they actually created lift. And so the whole sales pitch was, if you know how to fly a 737, because you've been doing it for 40 years, you can fly a 737 MAX. But they used software to control this additional pitch that you would get because there was lift coming from these, from these super large engines. And so, yes, it was a software problem, but it was also a conglomeration of errors prior to the software problem that led to them even having the issue to have to control the pitch in the first place. And when a pilot didn't know that was going to happen because the simulators hadn't been updated, they'd start compensating. And that's where you get this whipsaw effect. And then planes would crash into mountains or they'd tail spin because they, pitched too high. So anyway, it's just, yes, it's software, but it's also like the whole human element behind it, right? It's a social problem, not just a technology problem.
Training would have solved it. But
Training would have solved it, but the whole point was not to train them.
Yeah, exactly.
Oh yeah, and in this case, they did outsource, and it wasn't. Yeah, they outsourced it last minute. They fired all of the seasoned engineers because who needs them? And the rest is, they say, is history.
So Robin's got a question, Bob. How do you reconcile the need for experienced programmers with more than 5 years experience with frameworks that change at a much faster rate? Excellent question, Robin.
Frameworks are not the basis of experience. Experience is something else. You can pick up a framework. Anybody with a reasonable amount of experience can pick up a framework in a matter of weeks. So, doesn't bother me that the frameworks are changed. Now, let me say that differently. I don't believe that experience is what dictates whether or not you can adopt a framework. I'm not going to be hiring somebody because they know a framework. I'm going to be hiring someone because they know a framework.
What? Every job description I have says I need to know those frameworks.
Yeah, that's really stupid. Yeah.
Don't have 10 years worth of React. I mean, what good are you?
Yeah. No, I'm not doing that. Now, having said that, why do we keep on having more frameworks? It's not like we haven't explored this whole space 5 times already. Right? There are no new ideas out there. These frameworks keep on coming, and it's a rehash of old ideas. Same with new languages, by the way. Just rehash of old ideas. We don't have any new ideas coming in here, and we haven't probably for 30 or 40 years. So we keep on thrashing and thrashing and thrashing, and everybody has to keep learning and learning and learning. But what they are learning is they shouldn't have to learn, because it's just a rehash of old junk.
A different way of doing the old stuff.
Exactly.
Yep. Yep. Now, and again, whoever's watching the chat, you're going to see great discussions about the requisitions for more years experience than framework has existed.
Oh, yeah, that's real
and
common.
I've seen that over and over again throughout this career is, yeah, well, you know, that thing that's been out for 3 years, I need someone with 10 years experience on it. Dang it.
30 years experience of React.
Yeah, there you go. And if you've got it, well, maybe you're split personality. I don't know. All right. Well, Bob,
It's called resume padding, Rich.
that's the
All right.
problem.
I'm
Yeah,
gonna go see what my
educating-
wife is doing.
I will say, okay, one more thing I will plug. Craig, you called attention to it. We are, in fact, educating the recruiters right now. because some of them have been a party to some of this. So there you go. Question. Oh, Luke has another question. I'm fully sold on test-driven development and developed that way myself. Do you have any practical solutions on how to sell management?
You don't bother to sell management. It's none of their business. Why the heck does management care how you write code? You ask them permission to write if statements? Well, you know, there's this thing called an if statement. Is it okay if I use it? Right? It's like asking permission to wash your hands after going to the bathroom. You just do a test-driven development. You don't ask anybody. You don't ask for permission to refactor. You don't ask for permission to do pair programming. You don't ask for permission to clean up the code. That's your business. You're the programmer. You're supposed to know how to do this.
Luke, I think that's a great answer. I don't think you can beat that one.
Okay, well, let me push it a little bit further with the second half. Is
All
there
right.
a way to sell this discipline as I'm job interviewing and going out there and saying, hey, I do this thing, I think it's better. Please hire me over people who don't do this. Or should I just shut my mouth and not tell them about TDD in an interview process?
Well, it's always a risk to tell them about TDD because it's controversial. And so you're going to say it, and then a bunch of the other programmers are going to hear that and go, oh man, is this guy going to come in here and try and change everything? Now, if it were me, I would just tell them, yeah, that's how I do it. You want to know who you're hiring. Well, you're hiring somebody who does this discipline. And, you know, I'm probably going to be showing other people this discipline too, because it really helps. And then if they don't want to hire me, that's fine.
Yeah. No, and I think,
you may not want to work in that environment.
yeah,
That's true too, yes.
yeah. Okay, well, we're gonna let Bob go and have a little bit of evening left. It's getting later over there. 9 o'clock, huh?
Yeah.
We could have abused you worse. Thank you very much. It was
You're welcome.
extremely entertaining.
Yes, thank you.
Thank you
You're
very
welcome.
much.
A lot of fun.
Thank you.
I'm sorry I
Love your
was
books.
late.
Yeah, appreciate it.
Luke's showing off his clean code,
Yeah, I saw it. I got it. Yeah.
virtual signature.
Now here's this one. Yeah.
Who wins the signed copy for tonight, Rich?
Yeah.
Ah, dang it. Bob, that's in the mail, right?
He tried
All
to
right,
leave in
guys.
time, and we
He
couldn't.
was just gonna keep it.
Trust me.
Thanks again, Uncle Bob. It was fun.
All right, guys.
Thank you, everybody. Bye-bye.
Bye.
Thank you.